Starting off with a shameless plug, if you happen to enjoy Las Vegas and technology, the Dell EMC World's coming up May, so be sure to check out DellEMCWorld.com and join us there. A little background on myself. So I've been at the EMC and now Dell for about 6 years. So my principal systems engineer, which just basically means I'm a big geek. And now I get the opportunity to lead our go-to-market for data analytics. So taking a look at the entire portfolio of products from Dell EMC and making sure that we have relevant solutions as it relates to big data, analytics, and so on. I'm a huge fan of hardware. I like to hug things, see flashing lights, hear the hum. Forgive me, it's a thing, both in my professional life and my personal life. So I'm currently building, does anybody know what that car is? It's a Holden Commodore. I'm building the American version of that currently for a track car, really into gears, or I'm much of a petrol head, as they would say in the UK or in Europe. My background is mostly in applications, so actually Oracle and SAP, and then got into hardware about the last 6 years. I have a blog. I'm not very creative, so I'm into big data, and I have a beard. Therefore, big data beard seemed like an obvious choice. And then I do get the chance to travel quite a bit around the world for work, and although it may seem crazy, I do tend to take my family with me on a regular basis, so they go with Daddy on his business trips. And so if you're ever interested on how to do that effectively, we have a little personal blog called gowithdaddy.com with all of our travels. Clearly, you can see I have 2 very small children and a super hot wife. This is being recorded, right? I can show her that, right? Okay, cool. Okay, so the problem that we're going to help try to solve today is that oftentimes when organizations get asked, IT organizations get asked to build a big data platform, it can be a moving target, right? There's a lot of components, and we'll talk about those in a little more detail, but there's a lot that goes into designing and building a big data deployment, whether it's Hadoop or whatever platform you choose to use for analytics. It can be pretty challenging, and hardware is not an easy thing to figure out to do it right the first time. And so it actually ends up feeling like a little bit of magic, like dark magic. Everybody knows who that is, right? That's Severus Snape he's the professor of the dark arts. So we're going to try to teach you some of the dark arts of hardware as it relates to Hadoop. So my goal today is to provide you some basic fundamentals for sizing a Hadoop deployment, and then I'm going to share with you some general best practices, okay? Now we're going to start off with a couple of assumptions. First assumption is I'm hoping most of you in the room have a general understanding of this ecosystem that is Hadoop. It is a large ecosystem, lots of tools that go into the bag, and there's a lot of versions you must be mindful of. This is publicly available data. This is just telling you what the latest releases are as of the back half of last year as it relates to HDP deployments. So if you want to deploy any one of these things, these are the versions that are interesting, but I'm going to assume you generally have an idea what each of these do. Is that okay? Okay. The other assumption I'm going to make, or I'm going to hope that is true, is that you generally understand what hardware goes into a Hadoop cluster. So there's different usage kind of classes for a server within a Hadoop environment, but they really fall under 2 key hardware classifications. The first of which is what we'll call a master server, and think of a master server as the really important critical piece of hardware that does critical tasks. So it might be something like your name node, it might be something like an edge node where you're running Knox for authentication services, or it may be something as important as a supporting database for Ambari server or otherwise. These are typically servers that are enterprise class. You're using things like RAID to protect the data. Those are generally hardcore, like they need to be good servers because they're critical and they're not to be considered commodity. However, the other nodes that are in the class are what we call slave servers or commodity nodes. And these are where you run your compute and data nodes. These are things like a Kafka node. These are considered very commodity, very lightweight. We'll talk about builds and how we spec them out in later. But really, there's 2 key classes of servers, and this is important because this is going to be the basis for how I'm going to walk you through a really practical sizing example. Okay, and this is something. So just to clarify, if you're a Hadoop user today and you want to know how to build a new cluster going into it, this will help you. If you're an IT practitioner, this will help you level set and have a conversation with the Hadoop team and the people that want to deploy these platforms. And we're trying to normalize the conversation between practitioners, data scientists, and everybody that gets involved in these projects, okay? So here's a couple of generalizations. This is based on a lot of empirical data and some very strong opinions from yours truly. And I will guarantee you this, they are not 100% accurate at all times. There's a good saying that data scientists have, which is all algorithms are wrong, but some of them are useful. So consider this. I'm not saying that anything is categorical and absolute, because I'd be a jerk for saying that, because it's not. It's good directional. It gives you a guidance on some things that we've learned over time. And that's the goal here, is not to give you categorical answers, but point you in some interesting places. Okay, the first of which is everybody probably understands that the Hadoop file system protects data by replicating blocks of data at least 3 times, right? The standard is 3x replication. And that's cool because it gives you the concept of data locality, which is a good idea, but it also is bad because it gives you a lot of overhead, okay? And the HDFS file system will eventually get this concept of erasure coding. And if anybody wants to go deep into erasure coding and read Solomon algorithms and all that stuff, come chat with me later. But erasure coding is good because it is significantly more efficient than replicas. That's the critical thing that you need to know about erasure coding. Your performance is generally going to be about the same, but it's going to give you the same level of protection, if not better, but it's significantly improved efficiency. However, it's not in our current releases and the supported releases of HDFS today, so you have to assume 3x replicas. However, you have to assume from a sizing perspective a 4.5x factor for overhead. So HDFS is a file system, right? That's what the FS stands for. And one of the things you never do to a file system, regardless of which one it is run it full. If any of you have been through Hortonworks admin course for Hadoop, they say never run the file system over 75% full. It degrades your ability to deal with failures, to have free space for things like snapshot space. So the general advisement is assume 4.5x as your factor for overhead. Okay? Compression is cool and it helps. However, remember, compression does have a CPU impact. It's not free, so you need to take that into account for your sizing. And then some other interesting sort of generalizations is a throughput per core. So over the last 6 years, we've really been collecting data from customers on their clusters and looking at what is the underlying hardware actually doing, and what is a critical metric that we might find that would help us advise you folks on sizing these clusters. And an interesting one we found was the throughput per core. So generally speaking, a Hadoop cluster, regardless of the core type of core or whatever, it generally runs about 100 to 150 megabytes per second per core. Now, some may run more, some may run less. I get it, these are generalizations, but that's generally a good rule of thumb. However, the thing that we found was interesting is that a significant portion of the I/O that any particular core in a Hadoop cluster can drive is actually driven on HDFS data movement, the east and west traffic of moving data between nodes for the purpose of computation. So it's actually, we'll talk about it, we'll use roughly about a 50 meg per core throughput number because it's a safe number and it'll only cause us to have maybe more cores than we need than less. And I'm an engineer, so I'm conservative, so I like to have more than I need. Okay, virtualization realities, I get this question a lot when we talk about, you know, is Hadoop a workload that you can virtualize? The answer is yes, it generally works. VMware is a huge fan of it. That's kind of self-serving, I get it. But if you go deploy this stuff in the cloud, don't think for a second that it's not already virtualized. That's why there's the V in front of CPU from every cloud provider, is because they're virtualizing the compute instances. Unless you're willing to pay for dedicated hardware, which throws the cost way out in cloud providers. So cloud versus on-prem, it's a fun conversation to have. We're not going to go in a lot of detail here. You pick. If it makes sense for your business, great. I have some arguments that I think if your data is cloud native, it's born in the cloud data, maybe it makes sense to run in the cloud. If all the data you're going to be using is, let's say, IoT data coming from a small number of hubs where the data is being created, the provenance of the data is more local, then run in a local data center. Regardless, the reality is that you still have to size these things correctly, whether it's a virtual CPU in the cloud or it's on premise. If it's in a private cloud, you got to build it the right way. So we're going to use these same kind of metrics and foundations will work. Okay. And then our sizing approaches are going to be mostly based on building new clusters or replacing old clusters. We're going to we'll get a little bit into tuning, how you deal with some of the tuning issues. And the way we're going to do it is we're going to start with getting our sort of cluster size, and then we're going to get to the machine specs. Okay? All right, let's roll. So we're going to start with a capacity-based sizing approach. This is the easy one. I hope everybody brought their calculator in there, or a slide rule, or whatever you want to use. So traditional Hadoop clusters are deployed as servers with direct attached storage. That's what the DAS means. So for capacity-based sizing, there's a really simple formula that says, hey, if I have some amount of usable capacity, meaning the amount of actual data that I want to store in a cluster, that's the sizing, that's the metric I'm going to use to size my cluster. So the way we do that is we take that sizing, so let's say 100 terabytes, we multiply it times 4.5, which is, again, it takes into account the 3x replicas, the free space that you should always have in a file system. It allows for some space for things like shuffle sizing, intermediate space, and it also allows for a little bit of room for if people just do dumb things. People make copies of data. It helps protect good hardware engineers from things that people may do crazy. So we take that number. So if we take the capacity times 4.5, we divide that by the raw number of terabytes that any particular node might have. And we'll get to that. We'll talk about the kinds of nodes you might want to use. But in general, if you divide that number by your raw terabytes per node, you'll get your cluster size. Okay, so let's work an example, what that means. So if I have 100 terabytes usable, that means that's my 100. So that means I need 450 terabytes of spinning drives. Because again, in our worker nodes, we don't assume anything like RAID, it's all JBOD, just assume the raw terabytes there. And let's say that we assume, for rough numbers, 24 terabytes a server. That would be a server that might be a 2U server with 12 3.5-inch drives that are 2 terabytes each. So general kind of standard server that you might deploy. So if it's 24 terabytes per server, then how many nodes do I have to have? 450 divided by 24, well, it's a little over 18. But in these kind of numbers, we always round up for safety because, again, we don't want less, we want more. So in this case, if you told me I need 100 terabytes, I'd tell you, well, if you generally like the 24 terabytes per node, it's going to be about a 19-node Hadoop cluster in terms of worker nodes. So this gives us our worker node count. Does that make sense to everybody? Got a lot of cameras going off. This is good. I like it. Okay, so then we need to figure out, once we have our worker nodes, we need to figure out how many of those master nodes that we need, right? Remember we said there's 2 classes. There's the commodity workers, and then there's the dudes that do all the hardcore, really important stuff. So this is how we figure out our hardcore stuff. Funny story. This small cluster, this was actually one of the Hortonworks engineers and I worked on this a couple of years ago, and when he wrote it up there, he actually wrote joke cluster. So if you have an under 8-node Hadoop cluster, know that there's at least one person on the planet that would call that a joke cluster, and it's not very nice. So I changed the name. So anyways, what you figure out here is that if I said, again, in our example, I have 19 nodes, this is the number of nodes over here on this second column, then that tells me I'm going to have somewhere between 2 and 4 racks, but I need to have 4 to 6 master nodes. Does that make sense? Right? I need 4 to 6 nodes to do things like name node, secondary name node, edge nodes. Again, this is not 100% every time. I guarantee every single person in this room who's built a Hadoop cluster would probably have an argument one way or the other. You need more, you need less, or that's right. Anyways, it's a general rule of thumb, okay? And it's a pretty good sizing because the nice thing is if I build 4 to 6, I can make, because they're the same profile, I only have 2 profiles of servers, I could swap them in and use them for other things, right? That's the concept here, is that it's good generalizations that get us kind of in the right direction that then we can shift as needed. Does that make sense to everybody? So the output of this process would be something like this. It's that we now have a rack of stuff that we need to buy, and we know that we need to buy 19 nodes that are these slave nodes, and I need to buy 4 to 6 machines that are what I consider master class servers. Does that make sense to everybody? Cool, easy, right? Super easy. And everybody will have these slide decks. I hate it when people read stuff to you, so you will have this stuff available later. Okay, so that's the sizing-based approach. Hopefully that was simple and easy. I feel like it was. But then again, I wrote it, so it probably should be. So let's talk about an SLA-based approach, which is if you have a known metric around how much data you want to process per day, it's pretty good. It's a pretty good way to size a cluster. Because again, remember I said in those generalizations, I know, like you guys, we all know now how much throughput an individual core in a Hadoop server might be able to drive. So if I know how much data I want to process, which is a throughput number, and I know a throughput metric of what a node can do, I could back into how many nodes I need to get there, right? So if you know things like the amount of data you need to process in an amount of time, like let's say I want to process a petabyte a day, okay? Then we can size based on megabytes a second throughput. So basically what we do is we assume 50 megabytes a second again for each core. And again, that's a safe number because if I use a higher number, I'm going to have fewer cores, which may be bad. I use the low end spectrum, so that means I end up with more cores. So I'm likely going to have really, really good performance. And then I figure out data processing requirement divided by that 50 cores, or that 50 megabytes a second, which gives me my core count. Then you basically do some more simple math. You take your core count divided by how many cores would be in a typical server that you might like to buy, and that gives you your worker node count. So, interesting story, what will happen is one number, you can actually use both of these approaches in tandem and just go with whichever number is the highest. Okay, so let's use an example. So if I want to, how many nodes do I need if I want to process a petabyte of data per day? So let's assume that first I want to translate a petabyte per day to megabytes per second, because that's something that we're using in our metrics that are pretty easy. So that's basically a terabyte a day equals 11.57 megabytes per second. Google will do that for you if you need it. And let's assume that we're using a 2U, 2-socket server with 12 cores per socket. So I got a 24-core server as my standard sort of Hadoop server. Then that means I need a total of 10 nodes. Okay, so 10 nodes will give me 240 cores, which will be enough to give me the ability to process a petabyte per day. Now, that's a lower number than I said before for my 100 terabytes. So you start to get the idea that one of them, we had a 19-node server, and now we have a 19-node cluster, now we have a 10-node cluster. You start to see, pick the higher number for whichever requirement drives the larger number. Okay, so, and then again, and then you're also going to use the same chart that I gave you before for figuring out how many, so now we know 10 worker nodes. You'll use the same chart we had before for how many master nodes might you need. Because this was based on a petabyte a day of processing. We didn't even talk about how much capacity. So again, use the higher number when you go through both approaches. Cool? All right. So things that we typically see customers not putting in standard Hadoop clusters, things like the Hawk database, they've renamed it HDB or whatever. But anyways, Hawk databases and things like Impala can oftentimes be separated into higher performance clusters. Spark can obviously coexist. It ships, it's out there. We see a lot of customers deciding to run Spark in a separate cluster environment simply because the requirements for hardware can be different than your traditional MapReduce and HDFS cluster requirements, right? Higher memory, those kinds of things. And then Kafka, we also often see customers building significantly large Kafka clusters outside of their traditional Hadoop deployments. Okay, and any of one of these things we could have a conversation later, but these things typically just don't go in those standard off-the-shelf kind of conversations we've just had. Fair enough? Okay, so let's do some sizing for workloads. So everything we said before was kind of thumb in the air. We have a general idea. This is going to help us figure out what kinds of nodes we want to buy. So now we had the general idea of how many nodes. What kinds of nodes do we want to buy in terms of compute? So really it's about what are you trying to do with that Hadoop cluster? So there's a simple way to do it, which is I just ask simple questions like, are you expecting a lot of complexity? Are you doing things like machine learning, image processing, or natural language processing kind of stuff? Well, guess what? Those are pretty complex. They require a lot of CPU and memory. Jack up, like go to your vendor and say, I want more CPU and memory than maybe a 12-core, 64 gig RAM. We'll talk about it. So if you have a complex cluster that's going to do a lot of interesting complex computations, jack up the CPU and memory. If you're expecting to have low latency applications that are going to use significant amount of in-memory processing, then clearly if it's in memory, you want to have as much memory as possible. So jack up your memory ratio, right? Try to have as much memory in a server as possible to enable better in-memory processing and memory capacity. One thing we don't like to have happen is have things flush to disk if we're trying to process in memory. And then if you know that, hey, my Hadoop cluster is really, it's not doing a lot of really heavy processing, it's just doing batch processing, but it is super storage centric, right? I need as much capacity as possible, then you can have a lower amount of CPU and memory to disk ratio, right? You could have a lot more drives. You could use things like, large, 6 and 8 terabyte drives in your servers. So really, just think about when you start to say what kind of machine I might need, and when you talk to your IT practitioners, or if IT is talking to you guys, talk about the workload, because it has a massive impact. Because one of the things that you have to keep in mind is that if you start and you build a Hadoop cluster, you build this clustered environment, you need symmetry in those nodes for quite a bit of time as you grow. So you need to think about what your workload is going to be over time, because the simple answer when anybody says, hey, why is this, I want to make this Hadoop cluster run faster, the immediate answer is, well, just add nodes. But if you've added nodes and they don't have a lot of CPU and a lot of memory and they've got a lot of disks, you may be adding a whole lot of capacity that you may not really need. So so you want to build this thing the right way the first time. So we really have sort of four categories. Most organizations will be what we call a balanced configuration, which we'll talk about in a second. If you want performance or ultra high performance, you're going to have, again, lots more CPU and memory, 2U or 4U, or 2-socket or 4-socket servers, as many cores as Intel will give you. And then if it's a capacity-driven conversation, use big drives. Use as many of them as you can. Okay. So there's 4 categories. The storage-oriented sort of recommendation would be use a 2U server. Again, because you're trying to get storage, you don't need a lot of CPUs, so you can use a single socket box. Lower your memory, because again, it's all about capacity instead of about performance, so lower your memory count and use as many drives as your vendor will provide. Okay, that's if you want to have maximum storage with lower end processing, that's the way to go. A balanced config is sort of the standard that most folks start with. About 80% of, if you talk to Hortonworks engineers, about 80% of their customers start with what we consider sort of a balanced config. And that's a 2U dual socket server with typically 128 gigs of RAM is the recommendation. Again, these aren't always the same. Like sometimes somebody will say, you have to have 256. Great. Like 256 is fine too. And generally these clusters use the 3.5-inch SATA drives, because again, we're trying to get capacity, but a little bit of performance. It's kind of that balanced config. So 12 drives in a server is pretty good. And then if you want to go performance, it's really simple. We start increasing the amount of CPU and memory to disk ratio. And if you want to go really, really fast, then you're going to leverage technologies like flash media for storage, NVMe, right? You're going to have as much CPU and memory as possible, smaller form factor servers, because you don't need all the space for disks. Does that make sense? Cool. Awesome. Now, this process can be a real pain in the rear. And my hope is that we've simplified some approaches for you today, but I want to offer a really simple way to do this. And that's what we call Dell EMC blueprints. So Dell EMC's blueprints is really simple. We've done all this work in labs for years and years. We package this stuff and we'll show you how it works. What we do is we have these 3 concepts: ready systems, ready nodes, ready bundles. Just think of it this way. We take a workload like Hadoop, we run in a lab, we have Hortonworks and Cloudera engineers come in and test it with their benchmark kits, beat the crap out of it, say this is the right kind of configuration for this workload. And we have a variety of offerings. And we build those on top of either traditional servers from Dell's portfolio or things like converged and hyper-converged technologies, which are getting really interesting for big data these days. And if you want to build it yourself, great. We'll show you how to build it the right way using proven reference architectures. But if you're an organization that says, I don't want to know how the sausage is made, I just want the outcome, I just want to taste the tasty sausage, you just want to buy something, well, we have these things called hybrid cloud platforms that are out of the box, super simple to deploy, super simple to deliver and manage, that you can literally buy the outcome, okay? So we've aligned these blueprints across 4 key areas. The one that you will care about for this conversation is data analytics. And basically that means that we've gone out with folks like Hortonworks, Cloudera, and Splunk, and others to come soon. And again, gone through some significant rigor to make sure that we test our assumptions, the assumptions here, and give you simple outcomes, which is you get reference architectures, deployment guides. We've even gone so far as to, if you want help with the scripting for deployments across, regardless which platform we choose, we provide those to you as a service, okay? And if you're interested in things like interesting consumption models where you really like the operating expense model for cloud, but you want to consume the hardware on premise, we have flexible financial offerings that will actually allow you to have a very similar engagement with your controller and CFO on how you consume this hardware, okay? So currently our offerings for data analytics, for what you all care about, are these 6 things. So we have what we call a ready bundle for Hortonworks, and we'll go into it in a little more detail, and one for Cloudera today that is a traditional Dell server direct attached storage deployment, abides the similar sizing and everything that we just talked about before, and it can scale from small number of nodes to up to, I think our current one goes up to 9 petabytes is about the current scale that we've tested to. And then if you want to use something like Isilon, if you're not familiar, Isilon is a network attached storage platform that provides HDFS as a protocol. It's very interesting. The concept there is decoupling compute from storage. So you can scale storage when you need to or scale compute. Really kind of interesting. We actually have already tested it and have the exact same offering for that using Dell servers and Isilon storage. And then if you're interested in Splunk, we have some great platforms for Splunk using our converged technology. Splunk is an interesting platform for analytics, has some nice integrations with Hadoop, but we see them growing pretty rapidly, and we've actually seen customers like the cloud-like operating model that hyper-converged infrastructure provides. And then again, if you want truly to provide a big data as a service offering in your organization, the simplest way to get there is by using our product called the Analytics Insight module that's built on top of our native hybrid cloud, okay? All right, so let's talk about the blueprint a bit. So the blueprint concept is just this, it's really simple. It's that you all want to build a Hadoop cluster, but you want to make sure that it works and that enterprise IT will be happy and they'll have all the tools they need to go successfully deploy it. That's what this blueprint exists for. It is servers that are designed specifically for the Hadoop workload, networking components designed for the appropriate subscription rates that allow east-west and northbound traffic to exist in the cluster, using literally what is a really, really rigorous testing process to make sure it works well. And again, it's all the way down to things like scripting for automatic deployment. Okay, and again, it scales up to 252 nodes today is the current offering, but it certainly can scale beyond that should you choose. Now, the value of that is simply that it's just going to shrink the time to value. It's really simple, guys. If you want to deploy a Hadoop cluster, you can certainly go to a cloud and buy one, cloud provider and buy one. But if you want to deploy it on premise, we understand that your current IT providers may take time. We help accelerate your ability to go get what you need deployed very, very rapidly. And the best part is that if you don't believe me, and you don't believe your IT group, and you want to test this stuff, you want to see it in person, please come to one of our solution centers. We have them all around the world. Actually, interestingly enough, if you're really into high-performance computing, we have the world's 153rd fastest high-performance compute environment in Austin, Texas. It's called Zenith. It's pretty cool. If you hadn't seen the HPC 500, they track the fastest supercomputers on the planet. We have one of the top 500. But the nice thing here is that if you like what you heard today, or you say, hey, I've got a workload that I don't really know how to size it, I really want some help, you can use one of these solution centers to do a proof of concept, or you can certainly invite one of our engineers in to help do an assessment of your environment to provide you some recommendations that may go a little bit deeper than the basic fundamentals we've provided here today. If you want to learn more, we encourage you to visit dell.com/blueprints, or you're welcome to email blueprints@dell.com for lots more information. All right, we'll breeze through that one pretty quick. Hopefully we get this. I know there's a few more sessions before you get to go enjoy Germany's finest, but if you have any questions, be happy to answer those now. Question way in the back? I couldn't hear the last part of that, I'm sorry.
The comparison between the attached storage, like local disk
Mm-hmm.
or network attached storage or whatever,
Yeah.
versus the virtual sources like NetApp or something like that.
Yeah, so the couple, you kind of asked two questions. The question was, what's the recommendation on direct attached storage versus external storage? And then virtualization, kind of what's the recommendation on performance there? The first simple answer is on using storage that's not direct attached in server is please don't go use a SAN. If somebody tries to get you to use a SAN, it's not generally a good idea for Hadoop. You just have some design components that are wrong. Block attached storage for Hadoop generally stinks. It's fine for test and dev environments. That's okay, but it's not storage design. So if I were to walk in and say, you know what you need a VMAX from EMC for Hadoop, I'd be a liar and it'd be awful. Please don't do that. What you want is you want architectures from a storage perspective that are a couple of things. One, you want them scale out. So storage platforms that have two controllers are great for predictable traditional workloads like databases, but for scale out workloads for Hadoop, they fall over very quickly. And you want scale out, right? So you can just add a node at a time. And then the other thing you want is try to go as native as possible. So using SAN, again, can break things because it's not native to Hadoop. It's not how it's designed. But things like the way Isilon does Hadoop is actually quite interesting because it's a scale out storage that's network attached. And it's not trying to force a different protocol. It's actually translating the HDFS underlying RPCs. When a server asks for a block of data, it's actually translating those RPCs to POSIX file calls using their HDFS protocol and serving the data exactly as it expects to be served. And you can scale it out linearly. So you can start with as small as 3 nodes and you can go to 100, it'll be 400 at the end of this month. So you can go 400 nodes in a cluster. That's over 90 petabytes of storage. It gets pretty crazy. So generally the rule of thumb is for storage, if you're not using a traditional direct attached model, try to go as native as possible, which means something like a NAS that scale out, but do not use SAN. Is that fair? And that's, by the way, if you go to any of the events like Cloudera has one, their partner engineering dudes will get up and say oh, SAN's okay for virtualization or for test and dev, but if you're trying to run production, it stinks. And then the other question was around virtualization recommendations. The easy recommendations are don't oversubscribe anything. So if you're building virtual servers, do 1 CPU to 1 vCPU ratios to start. And then once you've deployed it, you may find that you can oversubscribe them a bit and you'll find a balance. What we found is, if you look at VMware's documentation, they found that typically somewhere between 2 and 4 X oversubscription on the CPU to vCPU count will get an optimal balance. Really depends on your workload, and you can tune that, right? Which basically means starting out, you run 1 virtual machine per server, and then as you grow, you may decide to increase that number up to 2 to 4 virtual machines per server, oversubscribing the CPU. And again, it just depends, right? There's not one exact right answer. Enable things like hyper-threading, but don't assume hyper-threading in your core count, because server vendors have a tendency where they say, like, Intel has hyper-threading, so this server actually, it's not a 12-core server, it's a 48-core server if you use hyper-threading. Don't use that in your core counts. Hyper-threading helps about 20 to 30% in performance as it relates to Hadoop, but it's not the perfect overlap that they think. Okay, did that answer your question okay? All right, go ahead. You got a question back here, sorry. Yes. So Extreme IO, no, because Extreme IO is a SAN, and the nice thing is that you at least hit on the scale out part of it, because Extreme IO's, if you don't know, Extreme IO is an all-flash storage appliance that's node based, so you can start with 1 brick or node and scale it to 8 today. Really, really cool storage for things like databases. Traditional Oracle, SAP, Microsoft workloads, it's awesome because it does have the ability to do inline deduplication, which is really cool, especially for things like VDI workloads. Love it. Not for Hadoop. It is absolutely not appropriate. The only thing I would say is if you wanted to build a Hadoop environment that happened to use something like Isilon for externally attached storage, you could certainly use virtual servers virtually attached to Extreme IO for things like the boot LUNs. So you need to have the boot drives, right? And then you might use it for things like the shuffle space. So if y'all are familiar with shuffle, when a Hadoop node gets busy and the memory gets full, it drops things into disk for the purpose of, like, hey, I'm going to need that in a minute. It's a very different workload than HDFS reads and writes. So HDFS reads and writes are typically very, very large block sequential reads, right? Because Hadoop uses 128 meg block size. You could change that, but a general rule of thumb. Shuffle space is extremely chatty. It's 4 and 8K reads and writes. The IO profile is totally different. So again, Extreme IO is interesting as a boot LUN and a shuffle space for a Hadoop compute node that was virtualized, but absolutely not appropriate for HDFS storage. Now, there's always caveats. Could you do it in a lab? Yes. Would I recommend it ever at scale? No. Is that categorical enough? Okay. And I love the product. I mean, it's one of ours, but it's not right here. That's why it's not up here. So most of the cloud versus on-prem conversations come down to really stringent requirements around data control. Like that's typically, it's either data control or it's a financial conversation. Some organizations really like the idea of consuming cloud services because it shifts from a CapEx to an OpEx, which gets interesting, right? But it's oftentimes, it is either really exciting or shut down really quickly because people start to look at the data control, right? Where is the governance of the data really happening? So those are, I mean, the conversation really quickly is I elevate it. So if it's an architecture conversation, it's the same thing. It doesn't matter. Like if you build it right on premise, you can build it right in the cloud. It's possible. You have the same kind of general sizing conversations. I would drive that conversation up and start to figure out, is it possible? Like, does the company have the legal capability to do this kind of thing in the cloud? And then I would drive it to a financial conversation to go to the controller or the CFO and say, are you trying to apply, like, are you trying to get to OpEx model? Okay, that's fine. If that's the case, does it also check this governance box? Are you cool with that? And then we have the conversation on hardware. I mean, because at the end of the day, these things from a sizing perspective, whether it's built in the cloud or on premise, you still got to do some engineering, right? That conversation is one that the executives have to decide. I generally think my gut is that I think the public cloud offerings are really, really cool for standing up test and dev environments, right? Developers get a chance to play, really quickly and easily testing things because sometimes IT isn't as quick to respond to a request. So I totally get that, right? But I think for most of the at-scale deployments, the large customers, my gut tells me most of them are going to do it on premise because either their governance will be a problem, or what they'll figure out is their enterprise IT shops probably can run it for a significantly lower amount of money than cloud providers will. Because, I mean, at the end of the day, no offense, we're all in it to make a dollar, right? we make money, like that's why they pay for people, but so does AWS and Google. It's not altruistic. So what they're trying to figure out is how do I virtualize as much as possible so I can run as much multi-tenancy and as many people on the same hardware as possible so they can make as much money as possible, right? And what happens is if you actually do a TCO, right, a total cost of ownership over time, you'll generally find that the cloud is typically more expensive. Especially given the fact that this is a sad note, but most people don't take into account the amount of time that IT operators cost. Right? So they think that we're free, right? As IT practitioners, like, oh, you guys don't count. But guess what? That's baked into the Amazon and Google and everybody's Azure prices. Is the cloud is operated by somebody, and that's baked in. So just do a TCO and have a legality conversation very, very quickly. Fair enough? Okay. Other questions? Yeah, back there. Sweet. You're like the Barbara Mandrell. Hey, sweet. I'm gonna send that guy a check. That's phenomenal. That's good to hear. Yeah, I mean, the point is, like, it's the same thing that the cloud providers do. They're testing their stuff. They know it works. Well, this is the way we do it, right? We do the blueprints because we know that we don't want you to buy a bunch of gear from us and it fail. We don't want you to fail. We want you to be successful. So we do a lot of work to make sure that you are successful. And thank you for sharing that you were. That is totally awesome. And I don't even know who you are, but I like you. Absolutely. Talk to your sales guy. We'll make sure that happens for you. I'm a lowly engineer. Sorry. All right, other questions or other awesome high fives like that are welcomed. All right. Okay, yeah, right back there.
What about networking?
Yeah, so we won't go super deep into it, but and that's one of my favorite things about the blueprints because I'm not a brilliant network engineer. I'm actually quite stupid when it comes to networking. But I will tell you that generally what we find is networking is vastly impacted by your deployment choices. So if you go with a direct attached storage deployment model, you will have a lot of east-west traffic between nodes. So the typical is spine and leaf topology, right? Lots of top of rack switches. Oversubscription rates, they try to keep, I think, below 4 is generally the rule of thumb. But if you go with a model that isn't direct attached storage, something like an Isilon, it's going to be a lot more northbound traffic because you're not moving data between compute nodes, right? Because although data locality, when you do those replicas, it's cool. In large scale clusters, we actually find that it doesn't happen as often as people think. Actually, if you Google the words data locality irrelevant, you'll find an interesting study published by some engineer or some students out of UC Berkeley's AMP Lab, which is really that's the place where Spark was invented. Like there's a lot of cool stuff that comes out of there. They actually posted a study where they assessed Facebook's largest Hadoop clusters, and they found that data locality happened less than 20% of the time, meaning when a job ran, there was less than a 20% chance that the data was actually on the server that was running that computational process, which meant that it had to do a read request from another server somewhere else to read the data into memory and process it there. So data locality, it's a cool idea, but it doesn't always happen. Yeah, so just from a network perspective, I would say I'll point you to some really smart network dudes. We like virtualized networks are cool, flat networks are even better. Cool? All right, I'm getting the 5 minutes on. We're done? Bang! Thank you all for coming, and hope you enjoyed.